Hi, my name is Gautamas. In this video, we are going to see about a mixture of experts. Before seeing about mixture of experts, let us see the what problem it is going to solve. The problem, the main problem here, mixture of expert is getting solved is fixed compute resource. So, to get more understand what is a fixed computer budget. So, when you are developing a model, large model or a small model, so when you start training a larger LLM model for a fewer number of iterations, it will be giving an best results. When you are comparing to uh, training a smaller model for more number of steps that is being trained at when comparing to a large language model. For example, if you are training an LLM model, for example, let's assume it's an 20 billion parameter model, you are training it for 20 iterations, and parallel you are developing a small LLM model that is being trained for more than 100 iterations. So even though the LLM is trained for 20 iterations, it will be giving a better results when compared to one this small language model. So this is why the computational resource is much important when coming to an LLM training. So this challenge is overcome by using a mixture of experts architecture. So what this architecture does is it while training it requires very less compute for training the LLM, and we can scale up this model or we can increase the number of data sizes while keeping the computer resource static. Okay, so this is the main problem that is MoE is getting solved. MoE is trying to solve this computer resource. So in MoE we have uh, two parts. One is a sparse MoE layer, and another one is a gate network or a router. Okay, so these two things will be there. We'll be seeing individually what each layer does. Okay, the first thing is sparse MoE layer. So sparse MoE layer, what here we does is, so generally the LLM that is having an transformation transformers architecture, right? So there they have an dense feed forward neural networks. So that will be there as an layers in the transformer architecture based LLM models. But here we will be having a mixture of experts layer. Okay, so here instead of dense feed forward layers, we will be having some certain number of experts. For example, LLM can have eight number of experts. Okay, so like eight layers will be there. uh, will be each layer will be acting as an expert. So here the term expert, so what does the expert means? Expert means same the neural network, but it will be an it can also be in sometimes the complex neural network. So either it can be a neural network same as feed forward new networks, or it can be an hierarchical MOEs. So hierarchical MOE in the sense, uh, we will be having a nested MoE layer. See, for example, in this diagram, so this is the parts. This is one uh, MoE expert layer. See, we have one expert network, and here we have another one expert layer. So which is a nested. Okay. So here we have an gating network. So what this does is, it will be choosing whether the input token should be passed either to this network layer, expert layer, or to this one. If we zoomed in and see what it will be having inside this expert layer is same another set of expert layers. So each expert layers will be having an same number of neural networks. So this is what we called it as an hierarchical MoE. Okay, so it's not just get an overview, that is enough for right now. We'll be deep diving into each one later. So the second part is on gate network or on router. So what this part of the MOE does is it routes the token. It sends to correct network as we see in the diagram. See, so this gating network will be deciding uh, the input token to be passed to which expert network. Okay, so this deciding factors will be known how it will be deciding it. It will be trained at. It also need to be trained at based on the tokens that we are doing in the initial stages. So we'll be diving deep inside it as well. So some of the challenges, right? While implementing this MOE, we are facing. So one challenge is struggle to generalize during fine tuning and takes to overfitting. So while implementing or while adapting this architecture, uh, okay, pre-training will be happen, and when we take this model right to the fine tuning, uh, so what the consumers will be facing is it will be getting overfitted. Okay, that is one challenge we are facing. And another challenge is in while inferencing. So all the parameters need to be loaded in the RAM, so the memory requirement are very high. So for example, if you are loading an Mistral 8 cross 7 billion parameter, right? So it will be requiring an huge number of virtual RAM to be processed. So all the 47 billion parameter should be loaded in the RAM. So the after that, after loading only, it will be getting processed. So here you may raise a doubt, right? So 8 here, 8 represents the number of experts that is this model is having, and 7 is the billion, 7 billion parameters. So each expert is having an 7 billion parameters. So 8 cross 7 will be an 56 billion parameter, but we have mentioned here 47 billion parameter. So it's not a mistake, it's the calculation behind this MOE architecture. So I will tell how this parameters are being calculated for MOE architecture. Okay, so generally in transformer layer, what we have is we have two layers. So one is in self attention mechanism, and second one is in feed forward network. So if we take 7 billion dense model, for example, here we have considered a Mistral 7 billion model that is developed using a transformer layer. So for the self attention and embedding layer, it will be around 1.5 billion to 1.75 billion parameters, and for the feed forward network layer, it will be around 5.2 to 5.5 billion billion parameters. So now if you come to this MOE architecture, what here it will be happening is the attention layer, normalization layer, and the token embeddings. So these layers will be get shared. Okay, so this is the main advantage of using the MOE architecture. So this will be getting shared, and only the feed forward neural network blocks will be duplicated, and it will be separated as an 8 different layers. So if we calculate the total parameters for this MOE architecture will be shared parameter plus number of experts parameter. So as we assumed here, the attention layer normalization and token embeddings will be around maximum it will be around 1.7 by billion for 7 billion model. So the shared parameter will be here 1.75 billion, and for each 7 billion feed forward layers, so it will be maximum around 5.2 to 5.5 billion parameters. So we are multiplying it with 8 into 8 layers, right? So 8 into 5.65 billion, which is around, if we sum up, it will be around 47 billion parameters. So, but if you adopt a transformation architecture, it will be around 56 billion parameters. So this is how the one major advantage. Okay. So what happens at the time of inference, right? So in MoE, all the 8 experts will not be working at the same time. Okay, while inferencing, we can have an parameter, like decide we can decide how many parameters or experts to be active at the time of inferencing. So here we are assuming 2 experts to be active at the time of inference. So the what the Mistral will be doing is it will be taking the top two routing, right? So it will be taking, and one expert active is which is equal to 5.125 billion parameters. So shared layer is 1.7 billion compute cost will be used, and for the selected experts, it will be around 2 into 5.125 billion, which is around 10.25 billion parameters. So only the compute costed will be charged for 1.75 billion plus 10.25 billion parameters, so which is around 12 billion. So only the inference cost will be around, it will be charged only for the 12 billion parameters. But uh, the compute resource, the RAM required for this resource, right, it should be all around 47 billion parameters, it should be there. So only here, while inferencing, the GPU processing resource used, right, it is only around 12 billion. So the key takeaway, right, instead of running two full 7 billion model, if you take, it will be around 14 billion. But using this MoE architecture, we could able to run with 12 billion parameters. So the attention compute gets shared, and only the experts compute resource alone is being get costed. So the main resource is utilized only for the 12 billion model alone. So the advantage is compute and the speed is being getting increased, but disadvantages, as we previously discussed, the memory and VRAM requires much, all the whole model to be loaded directly on the RAM. So then only it will be processed. So next, let's dive into the history of MoE. In MoE, we have, so this concept has been introduced in the year 1991, paper called Adaptive Mixture of Local Experts. So in this paper, we have an getting network determines the weight for each expert. Okay, during the training, both the experts and gettings are being trained. So that is how this author is being developed this MoE, and later in 2010 to 15, uh, experts are introduced as an components. So here, what will happen is all the experts will be inferencing. Like we have eight expert layers. So all the eight expert layers will be getting inferred here. But here, the layer is being getting introduced, and only that specific subnetwork can be turned on or off based on the training. So the gating will be deciding, based on that, it can, whichever the layer is needed for the activation, only those layers will be get used. So this is how the evaluation has been made. And next topic in MoE is sparsity. So sparsity, what does sparsity in MoE means? So it's works based on the idea of conditional computation. So what this does is allows some parts of experts to be run, uh, which allows this enables us to scale up the model with a fixed computational resource. Okay, for example, as in the previous example, we have around 47 billion model parameter, right? But we will be using only the 12 billion parameters. So that is how the scaling is worked with fixed computational resource. So but this uh, sparsity brings some challenges, some problems here has been introduced. So the problem is, see, for example, for a batch one, we haven't 10 tokens, and so the first 5 token is getting ended in one expert. Only one layer is being passed as an input, and the output is got from that one expert alone. So remaining 5 tokens, right? So it is get splitted into each experts, expert one, 2, 3, 4, 5. So there is some kind of uneven, right? So what it does is, this raises the uneven batch size and underutilization. The remaining experts are not being utilized properly. uh, so this leads to some kind of biasness in the model. So this is one problem we are facing while sparsity. So to solve this problem, uh, what uh, what we have done is, learned a gating network decides which expert to send a part of input. Okay, so gating network gets trained it well, and it will be deciding the input to be passed to which expert to be sent as the part of input. So here we have an one equation. So it's an simple equation, not a complex one. So the equation is y is equal to summation of I equal to 1 to the n. So g of xi and e of x. So g here is the gating network, and e is the expert network. So as per the formula, all the experts get rendered for all the input. Okay, so that is what the this formula represents. Okay, so what if the g value is 0, what will happen? So this is where we are introducing an sparsity. Okay, so if the g value is 0, we do not require that specific expert network to be operated. So the computational resource can be saved here further. And we are further writing this this condition, right? This condition can be written as an g of sigma of x, which is equal to softmax of x of vg wg. We also have other kind of gating mechanisms. So another gating mechanism, right? Like we have noisy top k gating. So what here in noisy top k gating does is, like we are bringing some random noise, okay, that can be tunable, and we can get the top k values. So here we have some formulas. Don't be get feared. It's a simple one, and no need to be uh, read. Simple. Just understand it. That will be fine. So here we are adding the noise. Okay, so h of xi, which is equal to x into weight of g into I, plus we are introducing here standard normalization, which is the noise is being added, and soft pulse x into weight of noise of I is being getting computed here. And here we are picking up the top k. So top k, and the vi is being returned it for the top k, otherwise the minus infinity will be returned as some value. So after that we are applying in gmax, softmax for this one. So softmax of keep top function, h of x is being introduced here instead of v value and k. Yeah. So some of the advantages, right, of adding this noise. So we can train and run the inference much faster. That is one advantage of adding the noise. But initially, uh, routing to be routing requires more than one expert was needed, because getting has to be getting needs to be learned. Okay. uh, need to be learned, like which input should be sent to which experts. So that learning, initial learning should be there, otherwise the model will be start becoming biased and it will be sending to one specific model.